The term rated speed is frequently heard in the context of electric trains and locomotives. But what does it mean? In the case of DC motors, the rotational force of the motor is determined by the current, while the rotational speed is determined by the voltage. More current results in greater torque, but there is an upper limit to how much current the motor's windings can withstand for extended periods. This upper limit is the rated current. Similarly, the voltage cannot be raised beyond a point where the insulation material's integrity would be compromised. When a train starts, it needs to exert as much tractive effort as possible for rapid acceleration, thus reducing travel time. Therefore, it is standard practice to maintain the current at the upper limit, known as the rated current. Unlike locomotive-hauled trains, EMUs on conventional lines have shorter power application times, and often operate with currents significantly higher than the rated current. As speed increases and the motor's rotational speed rises, the motor begins to act as a generator, opposing the current flow. To counteract this and continue the current flow, resistors or electronic devices increase the voltage applied to the motor. However, once the voltage reaches the upper limit that can be applied to the motor, the rotational speed can no longer be increased. At this point, the train's speed is called the rated speed, and the motor's rotational speed is called the rated rotational speed. Because the voltage cannot be increased further, any additional speed increase results in a decrease in current flow due to the motor's generating effect, reducing tractive effort. To overcome this, current bypasses the motor field windings with resistors, gradually diminishing the motor's generating effect and allowing current flow at higher rotational speeds, thus increasing speed. However, this also reduces the magnetic field, and consequently, the torque. If the field is weakened further, the motor's effectiveness diminishes, and further speed increases result in reduced current and torque. Maximum tractive effort is achieved from startup to rated speed, during which power output increases proportionally with speed. At rated speed, maximum tractive effort and power output are achieved, representing the train's peak performance. From rated speed up to the limit speed of weakened field, tractive effort gradually decreases, but generally maintains maximum power output. Beyond this point, as rotational speed increases, both tractive effort and power drop sharply, making the vehicle difficult to operate effectively at these speeds. Even in the currently predominant AC machines, the basic principles remain the same. In AC electric motors, induction motors and synchronous motors are used, both of which have a rotating magnetic element inside. In induction motors, this magnetism is created by induced currents, whereas in synchronous motors, it is created by coils wound into electromagnets or permanent magnets. Electromagnets require an external current supply, necessitating sliding contacts that wear out over time, similar to the drawbacks of DC motors. However, advancements in materials technology have led to the practical use of sufficiently strong permanent magnets, eliminating the need for contacts in smaller motors. Conversely, some systems use electromagnetic rotors to improve partial load efficiency. To change the speed of these motors while maintaining high efficiency, the frequency of the supplied power must be adjusted. In railway applications, trains accelerate from a standstill, requiring continuous frequency increase from near zero to the desired speed frequency. As frequency increases, it becomes harder for current to flow through the motor, necessitating a voltage increase similar to DC motors. When voltage is increased proportionally to frequency, the current flowing through the motor remains nearly constant, with this current being controlled to match the rated current. As in DC motors, the speed at which the voltage can no longer be increased is called the rated speed. To achieve higher speeds, induction motors can be driven at frequencies slightly higher than those required for proper rotation, allowing the speed to increase while moderating torque drop. This is akin to using a car's manual transmission in a half-clutch state, resulting in efficiency losses due to slippage. An alternative method to maintain similar effects without increasing slip is to raise the voltage while reducing the current. Instead of continuously raising the voltage in proportion to frequency, the voltage is increased in proportion to the square root of the frequency beyond the rated speed. This maintains a constant power supply to the motor, keeping within the control unit's power handling limits. Induction motors have efficiency limits, while synchronous motors' characteristics are determined by the control unit's voltage, current, frequency, and control method. In essence, the characteristics of AC motors depend largely on the controller, with synchronous motors particularly highlighting the controller's role. How does this determined rated speed affect vehicle performance? In electric trains, because there is no shifting gearbox, the rated speed is fixed by the reduction gear placed between the motor and the wheels. Let's compare the acceleration and speed changes of the Commuter 103 series, the Suburban 113 series, and the Express 183 series, all with a motor-to-trailer ratio, MT ratio, of 1:1 and a current limit set to 120% of the rated value. The 103 series has overwhelming initial acceleration, but it drops sharply around 30 km per hour. It falls behind the 113 series around 37 km per hour and the 183 series at 51 km per hour. For commuter and suburban trains with frequent stops, a higher reduction ratio is used to increase tractive effort at low speeds, resulting in a lower rated speed. Later, when the 103 series was deployed in rural areas for slow local trains with longer station intervals, drivers found it frustratingly slow to reach maximum speed. Conversely, for express trains with fewer stops and higher speed demands, a lower reduction ratio is used to increase rated speed and maintain some acceleration at high speeds. When observing actual speed changes, the 103 series reaches 40 km per hour in 20 seconds, while the 183 series only reaches 25 km per hour. However, as speed increases, the 183 series catches up, overtaking the 103 series at 60 km per hour and the 113 series at 104 km per hour. What about acceleration on a 16.7 per mile uphill gradient from a stop? Although acceleration worsens, the trend remains the same. On regional routes in the JNR era, acceleration after decelerating due to point restrictions favored the 113 series, making the 103 series less prominent. The 183 series also showed good acceleration but couldn't fully utilize its capabilities on regional routes with many 95 km per hour restrictions. How about locomotives? Let's compare the mid-Showa era's representative models, the freight EF-15 and the passenger EF-58. Since acceleration varies greatly depending on the load, we compare tractive effort. Naturally, the EF-15, emphasizing tractive effort at low speeds, has an initial advantage. In this example, the EF-15 operates at rated current, while the EF-58 notches up when the main motor current drops to 500 amps. Therefore, the EF-58 accelerates with an average current of 560 amps, demonstrating strong tractive effort relative to its reduction ratio, but it still doesn't match the EF-15. However, around 50 km per hour, the EF-58 overtakes, maintaining tractive effort with less drop-off at high speeds. The performance curves show smooth lines representing the average tractive effort at different speeds, but the actual tractive effort is jagged like a sawtooth. At this time, especially at high speeds, the locomotives had only 2 notches for field weakening. The rated speed determined by the reduction ratio clearly differentiated freight and passenger locomotives. With the advent of new performance electric locomotives, motor output improved, and field weakening could be set to as high as 40%, reducing torque drop at high speeds. Leveraging the strengths of both, versatile locomotives for both passenger and freight services emerged. The reduction ratio was selected to push tractive effort limits based on adhesion weight, which for an F-class locomotive with a 16-ton axle load is about 20 tons. Consequently, the rated speed of new performance electric locomotives introduced during this period averaged around 50 km per hour. Let's consider the EF65, renowned for its versatility from general freight to high-speed freight and blue train hauling. Comparing it to the EF58 when pulling 14 cars of the 20 series, the EF65, designed for mixed use, shows high acceleration at low speeds. The acceleration gradually decreases around 45 km per hour but continues to deliver consistent power, reaching the final stage of field weakening around 70 km per hour, where tractive effort rapidly declines. As a result, beyond this point, the EF65's advantage over the EF58 diminishes, occasionally even losing out. For express trains, frequent acceleration from these speeds is common. Thus, except for station departures, there were limited opportunities to capitalize on the EF65's high performance. The EF65 faced further difficulties when the maximum speed of sleeper expresses increased to 110 km per hour. It was challenging to reach this speed on flat sections when hauling a fully loaded 14-car train. The situation improved when the EF66 was assigned to haul blue trains. With its high output and sustained tractive effort even at high speeds, it provided the robust performance expected of express services. The EF66's performance and characteristics were roughly equivalent to an EF58 doubleheader. Had the world favored passenger cars, we might have seen daytime express passenger trains hauled at speeds close to electric multiple units by the EF66.